I designed a general-purpose remote controller from scratch. No kit, just KiCad. It has 6 channels, 4 analog and 2 digital. And trust me, this little device can talk to a receiver despite a surprising number of obstacles in the way, as we will see later in this video. In truth, this is part of a drone project I'm working on. But even if you are not building a drone, this controller is still useful. It can slot into all kinds of other projects too. In today's video, I'm going to walk you through everything behind it, how I built it and the results I got, so hopefully you can build one too. Let's start with a closer look at the PCB. As you can see, it's small enough to sit in the palm of my hand, and it has a little socket for an I2C LCD that displays useful info. Right now, it's showing the joystick positions. If I move the sticks up, down, and side to side, you see the numbers update live. Each joystick is really just 2 potentiometers, one per axis. As I move the stick, the resistance on each pot changes, and the microcontroller's IDC reads that as a voltage and converts it into a value from 0 to 1023. Pressing the joystick button works the same way, just digital. You see the value flip between 0 and 1. This code exists purely to confirm the remote is working correctly, but it also hints at the layout. 4 analog axes plus 2 buttons is a pretty capable setup for a quadcopter. The classic 4-stick layout, throttle, yaw, pitch, roll, covers full flight control, and the 2 extra buttons leave room for things like arm disarm and flight mode switching. That said, this board isn't a lock into being a drone remote. Update the firmware and you can point it at almost any project that needs 6 input channels. The brain of this RC is an 80MEGA 328P. If you spend any time in the maker community, you've heard of it. It's the same chip at the heart of boards like the Arduino Nano and Uno. Here, I pair it with an 8 MHz crystal and run it at 3.3 volts, which is the same architecture as the Arduino Pro Mini. Wireless communication runs through an nRF24L01 module. The one I use has an external antenna, which helps push the range further. The board also has a battery connector and an ESP header for burning the bootloader. Quick explanation for anyone unfamiliar. A fresh 8MEGA chip can't be programmed over USB until it has a bootloader installed, and that bootloader has to go on through the ISP interface. In my case, I used an Arduino Uno as the programmer, wired it to my board ISP header, set up the Arduino IDE, and selected Burn Bootloader. After that, I could program the board over USB like any other Arduino. Basically, I designed this remote to behave like a custom Arduino board, so it's easy to manufacture and just as easy to program in the Arduino IDE, a tool most of you are already familiar with. I could keep talking about this PCB all day long, but let's stop for now and see it in action. Since the drone itself is still a work in progress, I tested the remote on a different project. A while back, I built a programmable 8x8 LED matrix. I've got a full video on that if you want to check it out. This time, I hooked that matrix up to an Arduino Uno with its own nRF24L01 module and wrote coding files for both boards so they could talk to each other. The matrix is split into 4 quadrants. Pushing the left joystick up turns the first quadrant blue. Pulling it down turns it red. Pushing left turns the second quadrant red. Pushing right turns it blue. Pressing the left joystick button turns both of those quadrants green, and releasing it turns them off. The right joystick controls the other 2 quadrants, bottom and top right, the same way. Everything worked great on the workbench, but I wanted to see how far I could actually push this thing. So I took the receiver out to a square, lots of trees, a few houses, plenty of obstacles, set the LED matrix on a tree and started walking away from it with the remote in my hand, watching the connection status on its little screen. The signal held strong for a while, then it started dropping in and out, and eventually cut out completely. I measured the distance and here's what I found. A solid reliable connection out to about 40 meters. Between 40 and 50 meters, the link got flaky, connecting and disconnecting repeatedly. Past 50 meters, I lost it completely. That might sound short, but keep in mind that several trees were standing between the controller and the receiver the whole time. Then I tested again, this time swapping in an nRF24L01 module with an external antenna on the receiver end and mounted it on a nearby tree. After both boards finished synchronizing, I started walking again. The results this time were a lot better. The signal stayed strong out to about 100 meters, starting getting unreliable between 100 and 110 meters, and dropped out completely past that. Honestly, that second result surprised me. There were even more obstacles in the way for the test, and the link still held strong for more than double the distance just from switching antennas. I'm happy with this result, and more importantly, I know the controller actually works, but there are a few things I would change. First, bigger joysticks. The ones I used felt a little cramped, and I think bigger ones would better fit one's fingers. The second thing I would do is to add a physical reset button. I actually included one on the flight controller board, but completely forgot it here. This button is important for solving some issues with the Arduino IDE you may encounter. The third issue I will fix is a small mistake I made during design and only caught after the board came back from manufacturing. I paired the crystal with the wrong load capacitors. My 8 MHz crystal calls for a load capacitance of about 8 picofarads, and I use capacitor size for a different value, which throws off the actual clock frequency slightly. A couple quick things before we wrap up. As I mentioned, this remote is part of a larger drone project I'm building completely from scratch. I've already posted a video on the flight controller and I highly recommend you check out if you haven't. This whole project will be open source. Once everything is finished, I will release the manufacturing files so you can order the boards and build it yourself. And since this remote is a general purpose 6-channel controller, it's just as useful outside the drone project. My second announcement is that I'm now offering consulting. If you are stuck in a technical problem, whether it is PCB design, electronics, coding, or something else entirely, you can book a one-on-one call with me using the link in the description and we work through it together. The last thing I wanted to say is that this project is sponsored by JLC PCB, one of the biggest names in the PCB manufacturing. Their website makes it easy to go from idea to prototype and then to finished product. Just visit the link in the description to open it. Select PCB manufacturing, upload your Gerber and position files, choose how many PCBs you want as well as other parameters, and their tool will quote you a price and shipping options automatically in just a couple of seconds. They ship worldwide and the quality has been solid every time I used their services. That's why I highly recommend JLC PCB for your next project. Thanks to JLC PCB for sponsoring this video and helping make STEAM projects like this one possible. That's it for today's video. Hope you enjoyed it and picked up something useful. Before you go, check out the video on your screen right now. I think it will help improve your maker skills.